Hi everyone, and welcome to Slow Release Substrates to Control Matrix Diffusion of Chlorinated Solvents from Low Permeability Zones. I'm Kitty with EOS Remediation, Technical Sales and Support. A little bit more about who we are, EOS Remediation. Our headquarters is in Raleigh, North Carolina, close to the Research Triangle Park. We're a small woman-owned business that has been pioneering and developing in-situ bioremediation technologies, particularly emulsified vegetable oils, for over 10 years. We have both domestic and international patents and sales. We are a multidisciplinary firm with engineers, geologists, chemists, microbiologists, and other disciplines all mingled in. We offer technical support, design consultation, and start-to-finish project support. We're there with you from the beginning of your project all the way through to the end with any questions or concerns you might have about your site. We also do research and development, including product testing and innovative technologies development. A little bit about me, your speaker. My experience ranges from biofuels to wastewater to solid waste to chlorinated solvents remediation, as well as engineering consulting. My undergrad is in environmental biology, and my master's is in environmental civil engineering, where I did my thesis on bioremediation of PCED apples. What we will talk about today is what matrix diffusion is, as well as the limitations of current technologies to address matrix diffusion. And then we'll take a look at some extended release substrates and how they can be used for these issues, as well as a cost analysis. Diffusion. We've all seen this in chemistry class, so just as a quick reminder, this is the process where particles disperse to an equilibrium gradient. So they go from high concentration, like you see here in this animation, to low concentration over time. In groundwater, we typically see this as laminar flow, and this is driven by molecular diffusion. The matrix is the substance in which we're working in, which is the aquifer material and sediments. Heterogeneity is common in aquifers, the layering effect over time. And as you can see in this photo from PE Magazine's cover, you can have high K zones and low K zones, and they can be orders of magnitude in variance for your hydraulic conductivity. You could be all the way from a glacial till to a gravel and just have, like I said, orders of magnitude of variance in your hydraulic conductivity. So this can make sites very difficult to work with. What does this mean? How did these two things come together to form this issue? In this cartoon, you have your initial spill of PCE, and you have a DIN apple coming into the subsurface. As you can see, it rides down along the low K or clay lenses, and over time, it soaks in. So remember that something like PCE has an octanol water partitioning coefficient of 3.4. So it's very hydrophobic and it sticks strongly to the aquifer materials. Over time, you get fresh groundwater from upgradient, or you're cleaning up the contamination in the sandy areas. And then as this water becomes free of contaminant, the contamination down gradient changes. And the material that was sorbed to these low K zones come back out through diffusion, as you can see as the pink comes back out into the clean groundwater. So here you have matrix diffusion, diffusion of the contaminated material out of the matrix back into the groundwater. How can matrix diffusion affect your site? You're a consultant or a practitioner, and if you're seeing persistent contamination that you're failing to meet closure, and your frequent and prolonged operation and maintenance costs due to that persistent contamination. Taking a look at a best case scenario, you have a site starting off at about 11 milligrams per liter TCE. You go ahead and remove your source, as you can see here, with the elimination of the source around 4 years. After that removal, you see some downward trending in your concentrations. So within 10 to 15 years, you reach your MCL targets. It's still a long time frame, but you do eventually reach your target once you eliminate that source zone. What some of you may have seen of your sites or encountered this same scenario where you have a concentration with a source removal, but then you see rebound. So you get to a steady state eventually, and you never see that gradual decline in contaminant, and you never reach your MCL targets. Let's take a look at some real data. This is by Chapman and Parker, 2005. You can see here that a sheet piling was installed at the plume to cut it off, and then you see the concentration decrease. So here you can see that the lawn plume tailing reaches a steady state of back diffusion, and this is the matrix diffusion of the contaminant being released back into groundwater. There are some interesting models that have been put together and some source attenuation zone curves that give you a good visualization to picture this with. In this study, it was assumed that the average life for exposure was 50 years, which is representative for most late-stage source areas. The aquifer material basically has been in contact with the DNAPL for about a 50-year lifetime, allowing it to soak in. It's interesting, you can look at the PCE, and it has a long DNAPL phase and a short matrix diffusion phase, as compared to TCE, which has a short DNAPL phase and a long matrix diffusion phase. So this is basically a function of solubility. The higher your solubility of your contaminant, the higher your persistence. Taking a closer look at some of this data, you can see in the pink highlighted table, the matrix diffusion period for PCE on average can be about 40 years, and for TCE this is up to about 80 years. And the interesting thing to look at here is the percent of longevity of the source area that is matrix diffusion. For PCE, about 20%, because your DNAPL period can be so extensive. But for something like TCE, which keep in mind is a degradation product of PCE, it can be up to 70% of its lifetime. You can have your PCE contaminant degrade, and then back diffuse into the same sediments, and you get a cycle going. So PCE degrades into TCE, it back diffuses, and it carries on and so forth. Another thing to look at is its seepage velocity. The faster you're moving, the longer out the matrix diffusion is drawn. What are your treatment options? There's pump and treat, thermal, ISCO, surfactant or co-solvent flushing, and bioremediation. A lot of people combine these technologies as well in various different ways. Taking a look at the cost effectiveness compared to performance, this is a study by McDade et al. 2005 where he compared 36 different sites and normalized them based on performance. You can see that enhanced bioremediation is about $30 per cubic yard by volume, so it's a cost-effective remedial technology. Taking a look at sustainable treatment, not necessarily in the sense of being green, although enhanced bioremediation tends to be a green technology if it's using bio-based material or plant-based materials as opposed to petrochemical materials. We can look at thermal, ISCO, and even surfactant or co-solvent flushing as a quick mass removal, but they don't necessarily have a long sustained period. Depending on the solvent or surfactant you're using, they can have a sustained period. However, as in the graph we just showed, it's about 10 times more expensive than enhanced bioremediation. The basic concept of this value-added treatment that Adamson et al. Goes into, that's who the graph previously was from, talks about endogenous decay. With enhanced bioremediation, you produce a large amount of biomass, and that biomass stays in the subsurface and can kind of be recycled or reused to produce new biomass, which prolongs the life of the treatment. Also, you get diffusion of these materials into the low K zones. So just like PCE sorbs into the low K matrix, something like vegetable oil, which is also highly hydrophobic, will dissolve into the low K matrix as well. With strong reducing conditions, you get iron charging, and that prolongs the reducing conditions at your site. So the general rules that this paper has gone over for extended treatment period are considering to be about 1 to 4 year range. And you can see in that table that we were looking at plumes that have matrix diffusion periods for 20 to 80 years in some cases. So we really need something that goes beyond 4 years. Taking a look at substrate selection, biodegradation rate is controlled by compound structure. How bioavailable is that compound to microorganisms to break down for energy? We took a look at 40 different food-grade substances and their degradation rates, and degradation can be controlled through substrate selection. Taking a look here, this is soybean oil, and this is what's typically used in emulsified vegetable oil. In this graph, for comparison, the fastest release of reducing equivalents. Then taking a look at extended release substrates. These provide the longest source of reducing equivalents, as you can see here in this oval. So let's take a step back and look at conventional substrates. sodium lactate provides an initial pulse of reducing equivalence, as we can see here. And then looking at soybean oil as compared to other donors is showing a more sustained degradation and higher rates of microbial activity once it passes the initial lag phase. To put all these together for comparison, we see sodium lactate, we see soybean oil, and we see extended release compounds. You can see that the accelerated fermentation shows that for soybean oil, if we're going with the 3 to 5 year range, which has been shown in studies as well as in many field sites, and we compare it to the accelerated fermentation of the extended release substrates, it suggests a 10 to 20 year release. These graphs are a microcosm at mesophilic temperatures, so that's around 95 degrees Fahrenheit, or 37 degrees Celsius, and this test was done in accelerated fermentation and is not nutrient limited. The basic concept here is that if you have a substrate and you want to ferment very slowly to volatile fatty acids, so you want a slow release of hydrogen and acetate, or electron donor, to keep your microorganisms fueled for long-term degradation. So you want a gradual release and you want a slow, nearly constant supply of electron donors. The predominant concept, and I'm taking this from Adamson's paper and extending it a little bit, is that you want an initial pulse of substrate, say a sodium lactate type of substrate, then a steady substrate, say the soybean oil from the 1 to 5 year mark, to degrade the majority of the contaminant, and then this gradual release of electron donor for the 5+ years, so up to 10, possibly 20 years to address matrix diffusion. So that's that mass that's diffusing back out over long periods of time. Here at EOS, we've developed EOS XR, and the XR stands for Extended Release. This is specifically designed, based on the laboratory studies that I showed before, to address matrix diffusion and provide sustainable treatment for the 10 to 20 year range. It does include the soluble substrate and the soybean oil, so you get the combined power of all 3 substrates acting together. All the degradation rates meet up over each other for the extended release. And it also comes with a boost for the microbial growth, your nutrients and vitamins, in the same EOS micron size that you have come accustomed to with our other products. Take a real quick look at a cost analysis. At the end of the day, performance and cost are the key factors for most consultants, and we understand that about our clients. We have a site, just a fictitious site, a silty sand, an effective porosity of about 20%, about 12 milligrams per liter of TCE plume. Taking a look at a soluble substrate, we're probably going to use a 10-week reinjection cycle compared to an emulsified oil product. Here we're going to use EOS Pro, which is typically a 3 to 5 year cycle, and then EOS XR, which is a 10 to 20 year cycle. The difference between the soluble substrate and the traditional emulsified vegetable oil is dramatic. A lot of what that is every 10 weeks you're going out, mobilizing, buying product, shipping product, and injecting product. With an emulsified vegetable oil like EOS, you're every 3 to 5 years for your reinjection cycle, so you're basically minimizing the cost of mobilization over time. The idea with the extended release substrate, EOS XR, is that you're coming down even further and only injecting every 10, possibly every 20 years. These time frames are applicable, as I said before. PCE based on studies has been shown to last for prolonged periods of time, as well as TCE having a very long matrix diffusion period of up to 80 years. So the take-home message is that matrix diffusion causes prolonged dissolved phase contamination. This is the long tail, this is the rebound you may be seeing at your site. Bioremediation shows significant sustainability post-active treatment at that 4 to 6 year mark. However, the 4 to 6 year mark is not long enough to sustain treatment to address matrix diffusion. At EOS, we've come up with some extended release substrates that can provide long release and start addressing matrix diffusion. If you have any questions, please feel free to contact us. I'm Kitty at eosremediation.com, and please visit our website at www.eosremediation.com. We have product spec sheets and anything else you may be interested in our library. Also, feel free to give us a call anytime. Thank you for listening to this presentation on matrix diffusion.